I'm working at APC, and I am doing the coordination from the Virgo side to all this low latency activity. This consists of sending alert to the astronomical community to make a nice follow-up. So if you have any question about what I am talking about, please let me know now or later on during the workshop. So today we are going to deal with sky localization or gravitational wave events and the gravitational wave alert that we send to the astronomical community, or I mean more broadly as a scientific community. Okay.
You have to use the arrows. This thing doesn't.
Okay, that's fine. So first, a brief introduction about what is multi-messenger astronomy with gravitational waves. So we deal with transient phenomena that are connected to the valence universe, and they are coming from short timescales, so from milliseconds to several years. So there have been different sources to able to emit gravitational wave. And to emit gravitational waves, the source must be compact, relativistic, and asymmetric. And so here I summarize in kind of three categories that can emit in association to the gravitational waves some electromagnetic counterparts. So the first category are the merger that have been discussed during the different talk. And so far we have only identified this counterpart coming from that merger, either basically the counterpart from the neutron star merger that was associated with either a relativistic jet as a GRB or a more isotropic ejecta, which was a kilonova. But there are some models that expect other counterparts as pulse radio burst and so on. So the second category that we might expect electromagnetic counterpart associated to that are the collapse or the signal star. But so far, our instruments are not enough sensitive to detect this kind of gravitational wave, or we are waiting the collapse of supernova very close. So we are still not able to detect the gravitational wave from this kind of sources, but we already know that we can have some electromagnetic signal about that. And the last family that I point out is the neutron star instability. So of course this is much more difficult to detect gravitational wave, and we are not so sure that we can even detect it with a very high sensitive instrument. And so the counterpart associated to that is also under discussion. So this third family is very is not very well, we don't have a really good understanding about this third family. So that's why we are mainly concentrate on these two categories. Okay. So since 01 and 02, our detection helped to populate the stellar remnant diagram. As you can see in blue, these are the detection from LIGO Virgo on the black hole, and in purple you have the detection from the astrophysical side. And so here in yellow you can see the neutron star also detected from astronomical observation, and here in orange it is the detection from a gravitational wave that we detect with gravitational wave measurements. And so we are not so sure about how they originated this merger from black hole and the black hole. And so the problem in that with black hole is that we don't think that there should be an electromagnetic associated to that, whereas for the neutron stars we do not have any access to the in-spiral phase and all the properties coming from the gravitational wave signal, but also the relativity outflow with electromagnetic observation. So that is why in the next campaign and in the next decade, we would like to populate this diagram, and so this multi-messenger astronomy is very useful to populate these things and to have a better understanding that how this compact object was formed. So I would like to come back to our first case of multi-messenger with gravitational wave, which was 1708-17. So as I said, we have detected the gravitational wave emission from this binary neutron star merger, but we have also have access to different matter ejector. So first, the one from the GRB, which was much more a relativistic and narrow ejecta that helped to have a better understanding to acceleration mechanisms, okay? And so we also, so the astronomical community also detect the more isotropic ejecta, which was kilonova, and with the kilonova we have access to a very precise localization, because gravitational waves, and I will come back later on, give only a very not approximative localization. And also, so with combining a gravitational wave information when we have the distance and, for example, finding the host galaxy with observing the kilonova, we can make some multi-messenger study because gravitational wave gives us a distance, whereas with the kilonova observation, we have more the redshift. And so I would like to point out that here we are talking about transients and we are talking about make a rapid follow-up, but we need also to keep in mind that the long-term follow-up over months and over years help to have this global picture. And so what happened is that when the astronomical community follow up so the event over the months, we have a much more constraint under the radio about how the jet and the isotropic ejecta interacted. So what I say that we are in time domain astronomy, but the observation are starting from seconds from the gravitational wave to years to have this global picture. Okay. So now I will try to come back from another point of view to the 17017 event, looking at the timeline, because here we are talking about timeline. So what happened is that we had the GW detection in coincidence with a GRB funding by Fermi GBM. And so, the GRB signal was triggered 2 seconds our GW. But we spent like 5 hours inside our LIGO Virgo to send the first localization. And so at that point, it was not a very, very well localized. And so I think it was 10 hours after the GW signal that we sent the first precise localization, the localization sky map of, for example, it was about, I think, 40 degrees square or something, so that the astronomical community can point out and look on the sky if there was some counterpart candidate. So because the sky map was done with the 3 instruments, it was quite reduced, and it was quite easy to detect the host galaxy, let's say, because so the event was very close, and so there was only about 10 potential galaxies that was maybe corresponding to the host galaxy. So in fact, NGC 4993 was, if you combine with property of host galaxies and host gravitational wave, was maybe the 3rd. So basically, you should have made 3 pointing to discover the host galaxy. That is why many teams discover at the same time. But in reality, this was a very, very beneficial case. And so normally we have about 100 potential galaxies. So the challenge to find the counterpart is much more higher than it was for that case. So we were very... yeah, it was quite easy. So, as I said, the follow-up is not finished after a few hours, but so thanks to the effort at medium term over days and months, the X-ray and the radio counterpart have been found, and it's only the long-term follow-up that helps to understand where are the nature of the X-ray and radio counterparts. Okay, so this event is only the first one, and we hope that in O3 and in the next observation campaign, we hope to have a better understanding about different aspects. Of course, in LIGO Virgo, we are very concentrated on fundamental physics, on the black hole science, and so on. But all this effort to send the sky map is also to the fact that there are also some science about the electromagnetic ejecta. So right, we have only one case, and it is so. For example, we are not sure about the nature of the gamma ray that was emitted, where they come from, is still under debate. So it was also the first time that we observed clearly the kilonova. And so we need, again, to have more observation to constrain the kilonova properties. And as I said, we point out the kilonova 10 hours, the trigger time, so we didn't have the first observation of the kilonova. And so, in fact, there was already some mixture between the different ejecta nature from the kilonova. And so to understand more how it happened, we need to observe promptly, okay? So I think if we do it again for the kilonova, we need to respond as fast as possible. Also, more and more we will have events, more and more we will have information about population study. And as I said, this multi-messenger astronomy helped to have a more understanding of other subjects as cosmology and nuclear physics. Okay, so I think you have got my message. The idea is to circulate the sky map and the information as fast as possible to have this global picture, both from electromagnetic side and gravitational wave. And so that's why, since LIGO Virgo since the last decade, we have done this program to have this combined information from gravitational wave and astronomical community. So there have been 3 strategies employed by LIGO Virgo. The first one is to use our O-scale analysis, and we have a kind of data set of gravitational wave events, and we compare with electromagnetic transient found independently. For example, that was the case. You have a detection from LIGO Virgo, you have a GRB from Fermi, and you say, oh, the trigger time is okay. I mean, it is in coincidence in trigger time, and the localization are compatible. So this is the first approach. So it is kind of free. You just need to make the discussion how to extract these 2 information. The second approach that is done inside LIGO Virgo is a trigger analysis. Let's say that you have this sample, for example, a neutrino candidate or a GRB candidate, and then you're not going to use this all-cast search from LIGO Virgo. You are going to make a rerun your analysis around the time on the interval of the electromagnetic transients, because it helps to reduce your search parameter space in a gravitational wave analysis and to gain in sensitivity, for example, by a factor of, I think, of 2 for CBC searches. But this approach is very time-consuming, and we cannot do that for all the transients. So we are doing case by case, and basically we have a JUMP program with the space mission, Fermi and Swift, and the neutrinos. Okay, and so the last strategy is the EM follow-up. So here we have some online gravitational wave analysis. And so as soon as we have a trigger, we are going to send to the astronomical community, so that a posteriori, they are going to try to find some counterpart candidate. And so in my talk, I will focus much more on this approach, but if you have other questions from the 2-1, please let me know. So this follow-up, EM follow-up program started, I think, before 2010. And in the last campaign, we had these partners, astronomical partners, with some memorandum of understanding because our alert was not public. So there was across the world and also some space instruments. And here I would like to show this campaign because it shows how mostly all the astronomical group participated to that campaign in O2, and it was included more than 200 instruments covering the full spectrum, so electromagnetic plus neutrino and high energies instrument. Okay, and so so to see a bit the diversity of the partner is the fact that the telescopes in optical band covered, mostly our partner, half of them. So, okay, and so to this partner now in O3 we are going, as I said, to send the sky map. So how does it work? In fact, to construct the sky map, we check the different trigger delay between the different instruments, and also we take into account the amplitude of the gravitational wave signal and the phase. So if we have 3 instruments observing, then you can see that we can have 2 points, and using the amplitude and the phase, we can clearly reject one of these 2. Of course, if we have more and more, we have instruments, interferometers, more and more the sky localization is quite good. And so this localization accuracy is correlated with the SNR, the SNRs under the GW trigger on the different sites. And here I plot also the antenna pattern because we say that instrument interferometer can see the sky elsewhere, but in fact they are much more sensitive on the part of the sky than the others. So in fact it is the convolution, which is what I say, and what we call the antenna pattern. Okay. So to build this sky map, we have basically three pipelines. The first one is, so here I plot only the one that will give the sky map for the sky localization for measures. So the principle is that with this, because we have a waveform template, we can have also the distance. Okay. And so the first one that we can compute in seconds is a Bayer star that we call Bayer star sky map, and we're gonna to use it in the afternoon. And so this is very rapid based on approximation. Whereas within a day, when we have accumulated enough data, we can use our parameter estimation to produce this much more reliable sky map that we call line inference. So this comes only after 1 day or hours, depending on how we compute our parameter estimation. Okay, so in the last O2 campaign, we sent 14 alerts to the astronomical community. And here, this is the different sky localization area that we send to the astronomer. As you can see, the localization area of gravitational wave event is from a dozen to 1,000 degrees square. So it's not at all accurate. But you can see that when Virgo is contributed, so it can. So the thing is that it can contribute to the sky map, to the parameter estimation, but it is not necessary that if it does not contribute to the trigger, because the SNR is not so high, it can contribute to the sky localization estimation. So you can see that, for example, 170914 or 1708, 14 or 1708, 17, Virgo really help to have a better localization on the 100 degrees square. So that's why it is very important to have our instrument in science mode during a trigger, even if Virgo sometimes is not participating to the detection. And so just an example, for example, of the different time delay between the instrument, as I said, that is based on the sky, on how to estimate the sky localization. So for example, GW17 first arrive at Virgo, and then 22 milliseconds arrive at LLO, and then 3 milliseconds at LH. So that's why it is important to have Virgo very far away from the two LIGO instruments, so that it really helps for the sky map. Okay, so you're gonna play this kind of sky map this afternoon on the tutorial that Giuseppe, my colleague from Virgo, made it. And we are going to use these two sky maps, 1708 18, which was a BBH merger, isoscene from the 3 instrument, and the BNS merger. And so in that tutorial, you are going to see how to extract this sky map, looking at the information, for example, the distance and so on, and calculate how broad is the sky map, and also try to find the galaxy inside this sky map. So it's what we are going to do this afternoon. Okay, so now I will move on to the next O3 campaign. So we have kind of a different approach now in O3. You know that O3 starting just 2 weeks ago. So in O2, as I said, the alert was private. Here, the alert was public. So which means that if you subscribe to that we call the GCN, then you can also receive some alerts like everyone. So this is the first thing that is very different from O2. And the second one is that, based on the discussion with the astronomical community, we are going to send the sky map very promptly, within 5 or 10 minutes, as I said, to have this very rapid follow-up from the astronomers. And so in fact, we need to check, and Alan mentioned that we need to check really the data quality and check that it was not due to, it was an astrophysical event, it was not due to noise. And all this vetting on the alert will be done after we send the first notification to everyone. And so this vetting on the alert to see if finally it was a confirmed or a rejected event will be done within hours for a binary neutron star merger, or within a day for black hole merger, because there are less pressure for black hole because it is less probable that there is an EM counterpart. And also it needs a lot of investment from LIGO Virgo to be wake up to do this thing, so we prefer to wait a bit. So as I said, we have also a program to have this combined detection. For example, one single event in our data. One event found by only one instrument, but it is in coincidence with the GRB. In this case, it is not included that program, automatic program. So we are going to have some special telecom for this kind of special event, and if it is very interesting to make a follow-up, we are going to promote it and sending publicly, but there will be a delay because it is not in our standard program. Okay, so to be able to look at our LIGO Virgo alert, there is only one thing that you need to do, is to know the link to our LIGO Virgo user guide that we have done for you. That everything is described, in fact, how to connect, how to read our different message, and how to, so we have a tutorial this afternoon, but there are also some tutorials to deal with the sky map and so on. So I invite everyone that is interested to look at this user guide. Okay, so I will detail a bit the different notifications that we send to the astronomers. And so first, as I said, we had this kind that what we call notices, which is that can be read by a machine. So typically, the astronomer, they just digest it on the computer and send, for example, automatically an observation to be as fast as possible. And the second type that we have is stickers. So this is something that you receive by email, and that you can, this is human readable in this case, and then you can see how the alert looks like and so on. So here I describe only the notices and what information you can extract for that. So first you have, of course, so it is under that we call a view event. I don't know if you know that, but okay, you can ask me the question later on if you have some questions. So basically you have inside the date, the date and the trigger time. The author is the LIGO Virgo collaboration. Then you have an estimate about the photon rate, the link to the sky map, and also the group. So either so we have some results from the low latency analysis to find some mergers, but we have also this burst program, you know, to find, for example, gravitational wave from collapse of massive star and so on. So it is not the same because this use waveform template and this is not. So and then we have and then I will concentrate only on this part. So the gravitational wave emitted from compact merger, and then we did two indicators. So we are not going to release exactly the masses and so on. We are going to release some indicator about if it is likely a BNS or a neutron star black hole merger or black hole or something that finally is a noise. So we are going this indication over there. And also the second thing that we are going to release is if we think that it is, there is some ejecta around the merger. And this indication is quite interesting in case of a neutron star black hole merger, because in both cases you can have either electromagnetic or emission or not. And so what has been also requested by the astronomer is also to indicate if there is one of a compact object that is into the mass gap that his mass is between 3 solar mass and 5 solar mass. Okay. Okay, so I will come back. Okay, so O3, as I said, had just started, and there has been a lot of investment from LIGO Virgo to upgrade the sensitivity, basically double the sensitivity. In Virgo, we are around 50 megaparsec for a binary neutron star range, and for Enfant born 100 megaparsec and Livingston 130 megaparsec. So yesterday there has been the first alert sent. I don't know if some of you receive it. And so, all the things that I'm talking about happened because we sent the first notices. And so, yeah, I don't have the slide, but you can see the first notices. And so we claim that under this probability that the source belongs to a binary neutron star black hole BBH and noise. So in fact, the probability to be a BBH was over 99%, and the Haas remnant probability was around 12. So it was a bit incompatible because between this indication and this indication, and we are going to make some analysis to understand more the compatibility. But so all the effort from the low latency group was made, and so we were very prone to send this first alert to the world. Okay, so now I will just make 2 more slides. Okay, about so the strategy employed by the astronomers to find the counterparts, because it is not like the same as just a point on the sky, because of the wide localization or our GW event. So there should be a very global effort. So imagine that you have this sky map 100 of degrees square. So obviously you cannot say, oh, I'm going to use my VLT and find the host galaxy. There should be some different step before. So what's happened that globally there are the wide field instruments, for example, the gamma ray instrument that have wide field, they are doing survey, they are going to look if there are some trigger around the time of the trigger, biologically 100 seconds before, 100 seconds after. Either the neutrino, they are going to do that and report some trigger candidates. So gamma rays, neutrino, high energy instrument. The problem is that in optical, we don't have this wide field survey for the moment. So what the optical committee is doing is we scan the sky map. So most of the telescopes are below, the field of view is below 1 degree square. So if you want to scan 100 degrees square, it's a bit difficult. So that's why most of the team make a strategy to point out interesting galaxy into the sky map. So because we are standing the distance and we have the sky localization, they only select the galaxy at the distance plus or minus for the error and located in the sky localization. So this is how they proceed. So this number of galaxies, as I say, can be up to 100. That's why all the global effort is necessary to look at all these galaxies. And so then this first group, in fact, reports some candidates either in optical or in gamma rays. And so then there is another group, maybe, that is going to follow up this counterpart candidate, either in photometry, to look at the evolution of the photometry evolution, or more rapidly to make a spectra to understand if it is compatible with the counterpart candidate. And so what was the case for 17017, that this two-step helped to understand that that the counterpart was discovered, and then at longer time, as I said, you can follow up this candidate to characterize the electromagnetic counterpart over weeks and months and over years with radio. So just a note to our counterpart colleagues. So good luck to them. They are making a lot of effort from the other side to make them ready for the campaign. And so from the yesterday event, the astronomical committee already responded. So basically it was a BBH event, so mostly the gamma ray survey that is quite easy to follow up our triggers. And so yeah, in next year we hope that we will have new BNS events and find other multi-messenger case.